Hello, everybody. Welcome to our YouTube Live. Let's have a party. Who's here? Got some neat warm-up questions in the form of clickable images that should help you with your concept quiz today, particularly with questions number 6 and 7, the difference between transcritical and saddle node bifurcations. So we'll get warmed up with those clickable images in a couple minutes. But right now we're just having the who's here word cloud populate. And so definitely add your name in. Welcome. It's great to see you here. And having such a fun time all quarter with you all in the YouTube Live. And today will be no different. It's going to be a good one. And we're going to have a lot of questions, hopefully, about bifurcations, one of my favorite topics in all of dynamical systems theory. Couldn't get much better than this now, could it? Just getting my book ready to answer all your questions. Make sure I got enough ink. That looks good. All right, we'll just give 1 or 2 more minutes for people to join, and then we'll get started with the warm-up questions, and then we'll move on to the usual brainstorm list of what you want to see, and then the open chat, which is the best part. All right, looks like it's pretty start so that you don't see what other people clicked when you're trying to consider your response. So I'm going to activate this one now right after I hide the results here. Same polling results page, you should see my first question of a clickable image, and that is click where you see a transcritical bifurcation. This is from further exercise number 3. You may recognize it from the section that we're studying, and I didn't assign this one because I wanted to stay focused on kind of the other ones here that were a little bit simpler. But you can see if you're really if you're really enjoying bifurcation theory here, you can see on page 169 that we have a couple really intense bifurcation diagrams. By intense, I mean there's a lot of bifurcations all over that diagram. And when I was writing up your homework, I was like, this is wild. I've never seen so many bifurcations on this vast population here. That's crazy, right? That would never happen, I thought. But I will say that the one suggestion for a paper that somebody has shared with me already actually has very similar bifurcation diagrams in which there's just like a ton of stuff going on. And I was just like, wow, I had never really seen so many on the same diagram. So that's cool because we know that that can really happen in real life, and some research articles have complicated ones like that. And this clickable image practice is just to hopefully get you warmed up and used to just looking at a bifurcation diagram. It's not really asking you to do the analytics behind it, but just to recognize what kind of things we have going on. I got 7 respondents so far. I had 9 people put their names in the poll though, so last chance if you want to click. It's okay if you don't click the right place. It's okay. It's just for fun. And then I'm going to show the responses. Now I'm up to 8, 9, possibly 10. Does anybody else? All right, we got 10 responses. Let's see where people think there is a transcritical bifurcation on this diagram. All over the place. So one thing I'll say is that most of these bifurcation and the one that has the cloud of responses, it looks like there's about 4 people who correctly recognize that one spot. So do you see where you see that cloud up there where R is equal to 30 and where the X is equal to approximately 0.8? And somebody just changed their marker to that. Yeah, that's the transcritical bifurcation. I'm going to ask the same question to ask you where a saddle node bifurcation is. And like I was saying, this is kind of to help warm you up for questions 6 and 7 on the concept quiz. Because on the concept quiz, it asks you, what's the defining characteristic of a transcritical bifurcation? And same question about a saddle node bifurcation. Looking through the concept quiz, I was guessing those might be difficult questions. So I thought now's a good time to go over it. So now I can see that some people have moved the response over to the correct interpretation of transcritical bifurcation. And for those who want a reference to understand that a little better, I would have you go to page 157. So if you're taking notes on this or something, on page 157 right here on figure 3.40, it shows you the hallmark telltale sign of a transcritical bifurcation, in which two separate equilibrium, two distinct equilibrium points merge together into one, and then on the other side, they have swapped their stabilities. You see, because this equilibrium point right here on the figure that's remaining constant, it used to be stable on one side, and then on the other side, it's unstable. And then this equilibrium point, which is moving like a straight line, used to be unstable, and then on the other side of the bifurcation, it's stable. So transcritical bifurcation is one in which a pair of equilibria merge together, and then on the other side of it, they have swapped their stability types. Fun stuff. Okay, so you ready to try that one again? Same picture, but now I would like you to click where you see a saddle node bifurcation on that same picture. And hold on, I want to hide the responses there. Oh, I got a little technical difficulties, unfortunately. Okay, there we go. Now I'm hiding the responses so that you don't get bias from what you see other people doing. So you might not see the responses up just yet because I've hidden them. But I see lots of people responding, so we're up to 7 results, 8 results. If a couple more people want to just take a try, 9 results. Maybe one more person wants to throw their 2 cents in there. Remember, this is just for fun. This is just getting us warmed up to talk about what we're going to do today. And let's show the responses now. All right, that's great, great. Okay, at what is actually not a saddle node bifurcation, but it's called a pitchfork bifurcation. I don't know if they even taught you that one in the section. There's tons of bifurcations they haven't taught you about. Probably, maybe my favorite bifurcation might be the saddle node, or possibly the hop bifurcation. A hop bifurcation is covered in chapter 4 on oscillations, and that's in which a stable periodic limit cycle emerges. So there's some bifurcations that we have not talked about yet, but interested readers can look up. Can you all guess which one of these things amongst all that you've clicked on is actually called a pitchfork bifurcation? I bet you can guess because it looks like a pitchfork. So you know what a pitchfork looks like a normal fork where it's like a stick and then 3 tines coming out of it. And several people have clicked at the intersection of those 3 tines. And that is actually a pitchfork bifurcation, not a saddle node bifurcation. The other places that people have clicked on appear to be, if you look at it sideways, the vertex of a parabola, sort of, or a relative min or max on a polynomial function. And that's if I put my head sideways, right? Because I have to kind of think of this a little bit sideways to consider it a function. But the locations that people clicked on where r is equal to 5 and where r is equal to 15, those are examples of a saddle node bifurcation. The special thing that defines a saddle node bifurcation is the appearance or disappearance of a pair of equilibria, all of a sudden out of the blue. And that's why it was called the blue sky bifurcation. I think Ralph Abraham, one of the founders of chaos theory, came up with that description as a blue sky bifurcation. And that's because they just appear out of nowhere, out of the blue. And keep in mind that a saddle node bifurcation can be a place where they have appeared out of nowhere, such as the value r equals 5, or where they have disappeared. So there was a pair and then they suddenly disappeared instead of appearing, and that occurs at r is equal to 15. So the responses that people clicked on where r is equal to 5 or 15 are totally correct. There's actually another saddle node bifurcation that nobody clicked on. Does anybody want to change their response and click on that one? There's one missing, and I didn't see anybody click on. Yeah, you got it. Yeah, right. So at r is equal to 10, you can see a saddle node bifurcation kind of in the backwards direction, because there's a pair of equilibria merging to one and then disappearing completely. And again, the value at r is equal to 20. And you can research that one on your own. I'm sure it's in Alan's book somewhere, or it's also on Wikipedia. A really fun place to find lots of math. Okay, cool. So hopefully that got you all warmed up and excited about bifurcations. And now I'm going to give a few minutes to our brainstorm poll as usual. What do you want to talk about? And so you can either suggest something or you can vote up and down on any suggestions. As usual, I'll do my best to cover all the suggestions. Hopefully we have time for that, or at least point you to the right place where I may have pre-recorded some of the answers, because maybe some people still haven't seen all the videos by Thursday. And so sometimes if I see a question up there that I know I already recorded, I could just point you in the right direction that way too. So go ahead and take advantage of the brainstorm poll to just put in any ideas or vote on any ideas. And I'll give that a couple minutes to populate, and then we'll move on to the open-ended, which is my favorite question because that's where the conversation really happens on our YouTube lives. Oh, I miss who here. Just hi. Oh, all right. I'm not gonna say the student names on the recording, right? Because I make these recordings public in the hopes that some other people might be helped by what we did here. But so hi, I see you and I see your comment. Sorry you came in a little after we shut off the word cloud. But I will catch myself and not say any student names on the recording. Okay. Great. And go ahead now and enter in any of the questions, whether it's a homework question or it's a question just about either a figure or the reading, questions about the videos, or remember that there's an applied math question this week. We actually haven't talked that much about it, but I tried to write what I thought was a really interesting applied math question that explored saddle node bifurcations in the Ali model. And that's because you all told me you loved the Ali model so much that I wanted to revisit it, again, with the concept of constant harvesting like we did with the logistic model from week 7. And then I did that in comparison of 2 different populations that have 2 different growth rates. And I thought that was really fun. So I don't know if you've had a chance to look at it yet, but I had already recorded a video where I'm playing with the Desmos link that I had provided for that. So there's lots of resources to go along with that applied math problem. And that's just one of many things you might want to input questions for. So I see one question coming in for 3.6.2, but I'm sure that there's got to be more questions than that. So I'll give you step back and give you a few minutes to have that work while I read the one question that came in so far. Okay, great. So what I'm going to do, I'm still waiting to hear from you all about your questions. Usually I see the requests come in faster. And I don't know what's going on here that we only have one request. That's the day that I'm here to help you with your homework. That day. That's the day that I'm here to help you with your homework. So it's not too late to look at the questions right now. Yeah. Thanks for the comment. I see another comment, a request to go over the over-under method on another ecological or context example. One thing I'm thinking right off the bat would be I could go over the over-under method, how it applies to the applied math problem that I wrote, because the constant harvesting term could serve as the second term for the over-under method. And so I can definitely do it in that context, and also get you more oriented to that problem that I wrote. Give you all a few more minutes to look at the homework set and maybe consider more questions. And in the meantime, many people I see are voting up 3.6.2, and that question has to do with figure 340. So I'm going to copy figure 340 onto the board in preparation for our discussion of it, and see if you all do want to enter a couple more requests after that. Oopsies, that's 0. All right, now there's a ton of stuff up there now. I need specifics, and that's why that got voted down. I think that's appropriate. Let's see what else we got. 3.6.6, that's good. Further exercise, 3.6.6. So we got both of those to do. Nice, that's a great question. Ooh, further exercise 3.6.6, in which we investigate density-dependent harvesting in the logistic model. That will be a fun one too. Yeah, we can certainly construct a bifurcation diagram for that. Then we have a question about further exercise 2, which does have its own video. So the person who entered in further exercise number 2, I just want to put it out there that that has its own video. That's the video on hysteresis that I recorded. So I'm not sure if your questions are answered by that video or not, but I would try to, if I touch on that, cover what I didn't cover in that video. And now that looks like tons of stuff for me to get started on. Great. Okay, just a second. All right, cool. So now I'm going to turn on the open-ended chat. I feel like people have made really good use of the brainstorm by now, so that's great. Thanks a lot. And now I've got the open chat turned on, so definitely I'll try to think of questions to ask you so that we can get some engagement going, but also just throw any questions that you have or comments about what's going on right into that chat. Okay, so let's do it in order like we usually do, and let's start with further exercise 3.6.2, which I've already copied figure 340 to the board to talk about. So in further exercise 3.6.2, it says find the equilibrium population levels when A equals 600, 900, and 1200. Okay, great. Let's use the open-ended chat for you to contribute some answers too. So how about let's start with A is equal to 600 and let's see what people have to offer. If you feel like you know the answer for A is equal to 600, go ahead and put it into the chat. And here you can see that I've ticked off marks at A is equal to 500 and A is equal to 1,000. This is the place where A is equal to K. So for this example, the carrying capacity is 1,000. So carrying capacity always equals 1,000. Okay, so this is the place right here where A is equal to K. A is equal to K here. Okay, and so when A is equal to just 600, it says to use this diagram to find the equilibrium population levels and describe the stability. Okay, and kind of like what you see in the left-hand side of cases. Okay, so these are the phase lines, and here we're going to have A is equal to 600, and then 900, and then 1,200. Okay, and there's a bifurcation at A is equal to K is equal to 1,000. So the bifurcation is not really shown on the diagram. I mean, the bifurcation is not being asked for, but I just wanted to mark when I'm drawing these phase lines. It's a little too confusing when I put lines there. But part of the question, well, actually, they don't ask you what type of bifurcation occurs because this is the place where they introduce the transcritical bifurcation. But in between A is equal to 900 and A is equal to 1,200, we have the transcritical bifurcation that occurs right there when A is equal to K at 1,000. Okay, so specifically for when A is equal to 600, can anybody give me in the open-ended chat a ballpark estimate of what the actual values for the equilibria are? Somebody was saying that at A is equal to 600, there are equilibria at K and 0. But can we use more specific numbers? Like instead of K, could you say what value of X on the phase line that would be? So you're correct to recognize that X equals 0 is going to be one of the equilibrium points, but how many are there? And what are their values? Here's the figure right here, and I'll just use my green pen to mark off the value of A that I'm focused on right now. Okay, so right here, A is equal to 600 is right here. A equals 600. Okay? And I was kind of doing that in my lecture videos too. How would you answer for the point along the unstable line? Right, I think, so what it is just look at the line there and say, what do you think the value is right there? Actually, there is a way to know, right? Because there's always, usually, except for at the bifurcation value, there's going to be 3 equilibrium points. There's always going to be X equals 0, right? And then there's always going to be X equals K. That's the carrying capacity, right? So the other one is up here, X is equal to K. That's the carrying capacity. That's the other one. And then someone is saying, how would you know what the value is for the unstable? You see, we have the stable one at 0, the stable one at the carrying capacity. And how would you know what that value is right there? Well, the fact of the matter is that red dotted line is mapping the fixed point or the equilibrium point that occurs at X equals A. And because we know that A is equal to 600, which is what I see somebody entering in the chat, because we know that A is equal to 600 and that this red dotted line is describing the equilibrium value at A, then we know that there's another value right here, which is X is equal to A, which is equal to 600, right? And this one is X is equal to K. which is equal to 1,000. Yeah. Great. And also people are starting to try to classify them too. So right now we have the locations of them. Let me know if you have any questions left on how I knew the values of those locations. But remember, to get the stability, we really have to look back at the diagram over here. The bifurcation diagram is what, because that's a red dotted line right there, that means that that midpoint equilibria that is separating the two stable equilibria is an unstable equilibrium point. And I just want to watch out because I see that some people had typed into the chat that 600 is stable, but it's not stable. And one person did it right. They said that A is equal to 600 is unstable and X is equal to K is stable. But the thing about X is equal to K is that K, the carrying capacity, is a fixed value at 1,000. Okay, so the stable equilibria that represents the carrying capacity is actually at 1,000. So 1,000 is stable, 600 is unstable, and 0 is stable. And there you see the classic dynamics on a line for a one-dimensional system, which is that two stable fixed points must always be separated by an unstable equilibria. And actually that unstable equilibria, as we learned in section 3.5, serves as the dividing line between the basin of attraction for the lower stable equilibria and the basin of attraction for the upper stable equilibria. So unstable equilibrium points, they usually divide the basins of attraction for stable equilibrium points. I think that's another thing that I wrote into the concept quiz. And the basin of attraction for an unstable point is just the value itself. It's just that value of that equilibrium point itself. So the basin of attraction for X is equal to 600, which is an unstable equilibrium point, that basin of attraction is just the initial condition, X is equal to 600, because that's the only initial condition that will result in staying at that level. Okay, cool. So let's continue on to 900. So who wants to give me the answer for 900? It says to locate the equilibrium points and classify their stability. And I think 900 is going to be very similar to 600 because looking at the bifurcation diagram here, the bifurcation occurs right here where A is equal to K. And everything that's less than that value is qualitatively the same. Because everything that's happening, all the phase lines that happen for A less than K have the same quality that there exists two equilibrium points and the carrying, three equilibrium points. And the carrying capacity and 0 are both stable, and whatever the value of A is the unstable one. So A is equal to 900 is just another instance of that, and you're really correct. Thanks for adding that into the chat, is that and whatever represents A is equal to 900 is going to be the unstable point. Right, so X equals 0, still stable. Now, the value that used to be 600 is now up at X equals 900, and that's also going to be unstable. And then we got the X is equal to 1,000 up here, and that's stable. Yeah, so you see that this unstable branch, in both the cases where A is equal to 600 and 900, it's the same thing qualitatively. It has the same quality, stable, unstable, stable, with X equals A representing the unstable branch. And then after we go through the transcritical bifurcation, we're going to see something happen, a qualitatively different event happen in what that phase line looks like. So does anybody want to give the answer for A is equal to 1,200? I'll just mark that one off on the graph here. I didn't mark off A is equal to 900 because that's going to be pretty much the same thing as A is equal to 600. But you see on the other side of the bifurcation is our last case here where A is equal to 1,200. And it still seems like, as I read the phase line, it still seems like I have stable, unstable, stable. So it, at first glance, may appear that nothing really qualitatively has changed. But it has changed in what represents the unstable equilibrium and what represents the stable equilibrium. Yeah, you got it exactly right. Thanks for entering that into the chat box there. So we see that now the value of x equals k, the carrying capacity that used to be stable, has now turned unstable. And the LE threshold that used to be unstable, x equals 1,000, is now unstable, and that's because the LE threshold is all the way up here. X equals A equals 1,200 here is stable up at the top. Because it does still always have to go stable, unstable, stable. That pattern is forced upon it by the fact that it lives in one dimension. It's stuck on a line like that. So the basins of attraction for two stable equilibria must always have some dividing line that tells initial conditions where to go. But it is a bifurcation in the sense that what represents the carrying capacity has now turned unstable, where it used to be stable, and the LE threshold that used to be unstable is now stable. Now, before we leave this question, I would love to hear from anybody who wants to share. What do you think about that being somebody who has possibly studied ecology? Because I mentioned something about that at the end of my video on transcritical bifurcations, in which I kind of go through the same model, and then I kind of made a comment there at the end, and I don't know if anybody's watched it long enough to see that comment or if you're thinking the same thing, but it just seemed to me kind of funny what is ecologically represented as the LE threshold, for that to conceptually be stable, as you see as it goes through its transcritical bifurcation. Does that make sense ecologically? Could it possibly make sense? And I'm just not thinking about it because I'm kind of young in the world of ecology, but I wonder about that. So if anybody wants to share any comment, go ahead and do it. And in the meantime, I'm going to go back up to the brainstorm list, and I'm going to look for the next question to tackle. Now, keep in mind when you're thinking about this, that for this particular model, it's only a one-dimensional model. So somebody mentioned that, would that be like when one population overtakes another population? It's not possible for us to interpret it that way, because in one dimension, we just have the one population to deal with. We don't have multiple populations. It's a good thought and kind of brings us up into 2D state spaces like we saw with predator-prey or competition models, but it's not an appropriate way to interpret it here because we only have one dimension. Somebody else has said that conceptually it doesn't make a lot of sense to me for the LE threshold to be stable higher than the carrying capacity. I will have to think about it more. Yeah, and maybe I might want to ask Carrie about this, my teaching partner, because I thought the LE threshold was supposed to be some low value of the population below which it's hard for the population to survive. And the carrying capacity is supposed to be some high value of the population, which is kind of like the amount of the population that the environment wants to sustain. So when A is greater than K, you're kind of telling me that the number of the species in order for it to survive needs to be higher than the carrying capacity itself. But that doesn't make sense because the environment is only able to sustain the amount of the carrying capacity. That's what carrying capacity means. So to go through this bifurcation and say, well, my LE threshold has to be all the way up here, which is actually higher than my environment can even sustain population-wise, I just don't see how that's a realistic example. Maybe it is and I'm missing something, but that's just my initial thoughts on that. Thanks for sharing your thoughts, Sue. And I feel like the next thing on our list is going to be 3.6.6. So let's all skip over to 3.6.6, which is on page 162. And then we got one more comment coming in on that, which says, essentially it would mean that the ecosystem cannot support the species long term. I'm confused about the stability of that point because of this. Yeah, me too. Yeah, right. Because it says that the ecosystem can't support, because it can only support the carrying capacity. And so if the elite threshold is higher than that, then how is that even going to happen? That makes a lot of sense. And maybe we can bring it up a little bit with Carrie to see what she thinks about that. Cool. I'm glad that you're thinking that too a little bit, because I was just like, what? Okay, so here's what we need to do now. We're going to talk about exercise 3.6.6. And in order to discuss, I don't have a lot of hope. Maybe I can copy this one to the board. I'll try to copy figure 3.4.7 to the board. And then I'll talk about how I would try to answer question 3.6.6 based on looking at this. Although this 3D diagram that also tells you where the equilibrium points are located, as opposed to just how many there are, this would be more helpful when it says describe how many equilibria it has, whether they're high or low, and what their stability is. Oh, they're not actually asking you for the values. Okay, so I thought they were going to ask you for the actual literal values of x that represent the equilibria, but they're not. They're just asking you if those are high or low values. Okay, so we should be able to clear that up just with figure 3.47, because by low, they mean the refuge-only region, and by high, they mean the outbreak-only region. In the question where they say, state whether they're high or low, high would be outbreak, low would be refuge, and if there's 3 of them, that would be the bistable region. So for this exercise, we just have to situate ourselves in where we are in the bifurcation diagram for a 2-dimensional parameter bifurcation diagram that's right below the question. Okay, so let's think about that together. Yeah, maybe for this problem, it might be helpful for us to actually visualize the phase lines as well. So I'll kind of leave this board over here to draw some phase lines that correspond to the different sets of parameter values they have. Okay, like we were saying before, bifurcation diagrams will always have one axis at least that represents parameters and another axis that will represent the locations of equilibria points. But because this bifurcation diagram in figure 3.4.7 is trying to describe where the equilibria are located for 2 different parameters, that's why you would need to go up to 3 space in order to also illustrate the axis that says where those equilibria are located. Okay, so this instance of a bifurcation diagram does not contain the information of what are the values of the equilibria. Like I was saying, a proper one usually has. That's because we have too many parameters. So because we have 2 space of parameters, including the equilibria information would cause us to go up to 3 space. We can still learn a lot from figure 3.4.7 though. So this is 3.6.6 and it references figure 3.47. And what I just said is that this is 2D parameter space. Okay? This is not a 2-dimensional state space. There's actually no state space at all in figure 3.47. All we have is parameters, not states. That's why it's so important in chapter 1 to make sure that we understand the difference between states, which are the variables that depend on time and change in time, and parameters, which are supposed to be fixed instances that describe different situations. Okay, so we have one parameter, which is K, and that's the carrying capacity. And then we have another parameter, R, and that's the growth rate. Okay? These are 2 different parameters, and then we get this picture like this, where we have outbreak, and then we have refuge, And then we have bistable. Okay, so I'm not going to bother putting all the tick marks on this graph. I'm hoping that most of you are pairs in the question. I'm just going to ask you to share with me what part of the diagram are we living in? And the answer will be one of three things. Either you'll answer refuge, bistable, or outbreak. Because you see, those are kind of the three different places that we can live on that diagram. So for the first pair, in part A, k is equal to 10, r is equal to 0.1, please tell me, where do you think we are living on this diagram? Is it outbreak, bistable, or refuge? So this is part A. And I'll try to draw a phase line. Because even though we're talking about a two-dimensional parameter space, we're still focused on a one-dimensional state space. So that the state space diagrams are going to be phase lines as opposed to phase planes. Okay, and then I got a couple people answering. Thanks for your responses. And they're saying we're in the refuge region. Okay, so I'm going to try to situate myself to, and you're correct, right? Because when k is equal to 10, that's like down here. And when r is equal to 0.1, that's like right here. Right, so we're in the refuge region right here. Okay, so if we're in the refuge region, that's the region in which there's only one equilibrium point. And that equilibrium point is occurring for a low value. Now, just to match it with figure 3.48, the reason this thing has lines going all over it is because they're trying to have you consider what the phase lines look like for any point in that two-dimensional parameter space. And that's what I'm trying to draw over here, is I'm going to draw the phase lines. So if you can imagine on this figure, try to recognize which one of these little balls with a stick coming out of it represents the phase line that I'm going to draw right there. Right? So here you can see that the r-axis is right there and the k-axis is down there. K is equal to 10 and r is equal to 0.1 is probably one of these ones right here where there's a green ball at the bottom and then there's no other balls. Okay, so low x and it's stable. Okay, so when it says describe how many equilibria it has, there's only one. Is it low or high? It's low. What's its stability? It's stable. I kind of used both of these diagrams to answer that. If you really, really wanted to know exactly what that low value of x was, that's when you would probably go back a page and implement the over-under method and locate the place where the blue line intersects the red line only one time. So the first case for part A of this question, your over-under method graph would look like this. They would intersect at some low value of x. By the way, when I made that video, I also created a Desmos activity for you to be able to easily do this. So if you want to hop over to that video, my video about the spruce bud, where you can see values for k and r, and you'll see that intersection point, and you'll actually on Desmos be able to pinpoint exactly where that is. Let's move on to part B. So I said 3 people answered refuge correctly for that one. So how about part B? Who wants to give me an answer for that? Which part of the diagram are we in for part B here, where we have k is equal to 25 and r is equal to 0.6? And then what does the phase line look like? Outbreak? Oh no! Have we hit the outbreak only region? Let's see if anybody else wants to answer that too. I think you're right about that. Yeah, kind of if I just follow along with the figure in the book and it shows the tick marks, looks like k is equal to 25 is around here. And then it goes all the way up to r is equal to 0.6, which is up there. And so our second point for part B, here's our point for part A, all the way up there in the outbreak region. Right. And several people have said outbreak, right? Somebody had a typo and it says put break. That's funny. So what do you think the phase line is going to look like to play along with that part of it? My other one, when I was in refuge only, I just had the one low X. Now when I'm in outbreak only, I just have one fixed point, and that's a high X. And it's still stable. Once again, if you click on my video where I'm providing that link to a Desmos activity, you can just enter in these values for K and R, and you'll see the situation. What that Desmos activity does is it instantly draws a picture like this or like this for your different situations. And if you do that, you'll see that now you're in this black line situation where you're only intersecting once, but it's all the way over here in the outbreak zone instead of just being in the refuge zone like we see above on that picture. Okay, great. Now let's go on just the last part, part C here, where we have 20 and R is equal to 0.4. And looks like they're probably giving us one of each, so I bet you can guess which situation that is. Go ahead and enter it, though, if you want to play along. K is equal to 20 is going to be right here. And then R is equal to 0.4 is going to be here. And so right here, we have part C in the bistable region. Right, just like you're typing in. Right, great. So in the bistable region, it's a little bit tricky because you have to know that even the word says bistable and the word bi makes you think of two, like a bicycle, there's actually 3 equilibrium points, okay? So bistable regions have 3 equilibria, and that's because the middle one has to be unstable. In order to support 2 stable equilibrium points, they must be separated with 1 unstable equilibria so that their basins of attraction don't get all confused about which way to go, right? So the unstable equilibria is what separates the basins of attraction for the 2 stable ones. That's why it's called bistable. And so that's the region where we're going to have 2 stable ones. We're going to have a low X and we're going to have a high X. And those are both going to be stable. That defines the basins of attraction for each of these stable equilibria right in the middle right there. And that, I'll just call that a middle X, and that's the unstable. The unstable equilibria are not usually observed in real life, and that's because the basin of attraction for an unstable equilibria is simply the value, the one singular value of that unstable equilibria itself. That's on the concept quiz. So you're not really going to see it unless you just hit the nail on the head there and you had started with exactly that amount. You're never really going to see that. What you're going to see is you're going to see in real life a tendency either towards the high or the low steady state or equilibria, depending on which side of the line you're on for the unstable equilibrium. So it's still useful and it's kind of observed in that way as a dividing line, but it's not usually something that things stay at. Okay, cool. Hopefully that took care of 3.6.6, which is a big request on there. And then the next thing that we have is I see a request for further exercise 30.6.6 and further exercise 3.6.2. And it would be nice to go over the over-under method in another context. And I'll see if I can just squeeze in that request for the over-under method review as I go through some of these other requests. Actually, the over-under method would be a great way for us to tackle further exercise 3.6.6. So since I see that request in there so much, I'm going to go ahead and skip over to exercise 3.6.6. And I'll also say that I will return to see what kind of questions you have about 3.6.2. And if anybody wants to ask me something more specific about this, since I already made a video about this one, I wonder if there was anything missing from the video, if anybody has seen it and still had a question after that. I'll save that for the end. in the hopes that we can get a little more narrowed down in the request for that one. But 3.6.6, I'll do that one full out, and that will be a great place to illustrate the over-under method in a separate ecological context. Go ahead and read over the problem while I'm erasing the board here, so you can get ready to talk it over together. I have not worked out this. Okay, so I'm going to call this one Logistic Model with Proportional Harvesting, and that's because, to read the story to you, it says, suppose that in the absence of predators, a population grows logistically with a growth rate of 0.75 and a carrying capacity of 1. Also, a fraction h of the population is hunted each year. Now, can you tell what's different about this problem versus the logistic model with constant harvesting problem that I introduced in week 7 in my applied math problems that I wrote? Now's the time where I really want to hear from you, because I'm going to try to write the differential equation for this system. That's what part A tells me to do. And I know how to write down the logistic model. I've been doing that for a while. But how am I going to describe mathematically the concept of a fraction h of the population being hunted each year? What does that harvesting term look like, which I'm describing as proportional harvesting, to make sure that you see it's different than the constant harvesting that I had introduced before? Remember when I did just minus c and we were kind of raising it and lowering it? This isn't that. It's not just a minus c, because it's not just a fixed amount of animals that are being harvested per year. It's a fixed fraction of the population being harvested per year. So I'm waiting to hear from you in the chat box here about what you think the harvesting term looks like in the differential equation. Okay, so in part A, we're going to write down the rate equation for the system, and it gives us the R, and it gives us the K. Just to emphasize what I did with the K, even though it seems a little silly, x over 1, right? And then minus, what goes here? That's what I want to hear from you. Okay, and whatever goes right there. So I see somebody wrote 1 into the chat, and I think that you must mean the carrying capacity is 1. Here divided by 1. Even a little bit silly because x over 1 is just x, so I could have just written 1 minus x. But what am I going to do with this new letter h? This new letter says the fraction h of the population is hunted per year. That is what I'm asking. X over a minus 1. Remember that you're going to want to use the letter h. In this harvesting term right here, this is going to include the parameter h. Right, so we're really trying to match this with the problem. So I see that somebody shared an idea of using x over a minus 1, but you don't want to add any more letters. They didn't give us any letter called a, and I don't want to bring in any more letters than what they already gave me. Right. So we're trying to think of an idea here, and someone's put 1 over h in there. Somebody put 1 minus h over x. Neither one of those is exactly what I'm thinking. Let's put it let's think about it maybe with a specific value. Okay, because it says a fraction h of the population is hunted each year. Okay, so what if half of the population was hunted each year? What if I took out half? How would you describe half of the population? What would you write? That's what I'm trying to give you a kind of a leading hint. Like, so for example, if h is equal to 1/2, then half of the population is harvested each year. So if we were going to remove half, how would you say that in math? What would you say if your h is the fraction? Yeah. So, yeah. Okay, I see somebody put it in there. Right. So what I'm looking for here is 0.5x or 1/2 x, right? Because the fraction is h, right? So if h was equal to 1/2, that would mean I'm going to take out half. And if I was taking out half, that would mean I'm taking out half or taking out half. Like that, right? Does that make sense? And that negative term right there is what we're going to put in the double question marks right there, because it's trying to describe how much are we taking out. And it, like, for example, if we were taking out half, that would be 0.5 of x. Remember, when I say the word of in math, that usually equates to multiplication. So when I say half of x, I mean 1/2 times x. Okay, and so what I see as the appropriate response out of what's being shared in the chat is the 0.5x. That would be the case of half. So now, knowing that that's in the right direction, how would you generalize that now to saying, what if it was just h? And I didn't give you a number for h. What do you think the term would be now? So now, just use h as a letter. Instead of replacing h with a number like we did when I work with just an instance of it, so I kind of give myself a number to work with, and then I see what that would yield, and then I go back and I replace it with what the letter was, and now lots of people have it right. It's h times x is what's getting removed. The tricky part here is that h is already in a fraction form. So you don't want to do h divided by x, because then you would be doing fraction over fraction, okay? So just watch out for that, because I see that there's kind of a battle between whether we want to multiply x by h or whether we want to divide x by h. H is already a fraction. You see, like when I said h is equal to 1/2, and so I just multiplied it by that term, and so that's correct, right? We're going to do hx, right? So now we're going to remove hx. So we're removing h times x. Okay, so we're removing h times x, then what goes right here is minus hx. Minus hx. Ta-da! We did it! Yay! Okay, cool. So then we have the minus hx term. And I'm really glad we're going over this problem too. Thanks. Yeah, you can just type your thoughts in there too. It's so nice to be able to hear from you. Otherwise, I feel like I'm just talking to myself in an empty room, and that gets kind of weird. So thank you for just saying what's on your mind into the chats there. I'm so glad we're going over it too. And hopefully everybody understands how we came about the answer to part A, which is basically your classic logistic model, but the new thing we came up with was minus hx. Okay, so now it says, construct a bifurcation diagram for this system with h as a parameter. What kind of bifurcation do you observe? And then we have to change r to 0.5 and do the whole thing again. Wow, that's a doozy. Okay. Before, I would never try to attempt a bifurcation diagram before looking at my typical analysis, which is the x versus x prime graph. Because I need to explore that graph to get a feel for how the system is acting for different values of h before I seek to summarize all my findings with a bifurcation diagram. Because that's what a bifurcation diagram is. It's kind of like a summary of every different type of phase line that can possibly happen for different values of the parameter, right? So I'm not going to go there yet in part B. First, I'm going to do my classic x versus x prime graph. And I'm going to see what kind of stuff happens there. Okay. Okay. Ah, geez. This is, oh my gosh. Hey, nobody told me that I was missing an x term this whole time. Hey, there needs to be an x multiplied by that r there. Watch out, everybody, including me. That was not correct. Don't take me on blind faith here, because I make mistakes too. Okay, there needs to be an x right there. And then it goes 1 minus that. Watch out. We almost had a typo on the board there. Okay, so now let's explore what this system looks like for different values of the parameter h. So let's explore the x versus x prime graph. And that kind of tells us where all of our equilibria are. Okay, so here's x prime. Let's see. You know what? I'm going to have a hard time graphing this in my head unless I try to simplify it a little bit. Because I don't know if you're able to graph this in your head. You know who's really good? And you're at your computer, not at the whiteboard like me. I would say at this point, pop open Desmos.com and type in this equation. To make it easier to type in, come on, x over 1 is just x. So just type it in like that, okay? Type that sucker into Desmos and then make a slider for h and see what you get there, okay? Because that's what I'm going to kind of do, but it's no fun just trying to do the whole thing in your head. So let's all try that together, right, as we explore this problem. So I would encourage you to do that, which is type it into Desmos. I'm going to try to write it. I'm going to try to pull out this common factor of x and see if that doesn't help me a little bit. So if I pull out that factor of x right there, I have 1 minus x minus h. Okay, and instead of writing 1 minus x minus h, I'm going to rearrange the terms here to be 1 minus h minus x. And that's because now I can see its roots, right? I can't graph a parabola unless I really have an idea for whether it's up-facing or down-facing and where the roots of it are, okay? So I can see that I have roots here at x equals 0 and x equals 1 minus h, okay? And like all good logistic models, it's a down-facing parabola. So it's a down-facing parabola, and it has its roots at x equals 0 and x equals 1 minus h. Okay, so I'll just draw generally what I think it's going to look like, right? So here's a root. Actually, there's going to be different instances. Let me draw the, I kind of see in my head 3 different instances that are going to happen. This root x equals 0 is not going to change. That's always going to be at 0. Different cases for the root x equals 1 minus h, right? There's going to be the thing that I thought of right off the bat, which is that it's going to look like this, right? Where here's the root 1 minus h. And that's going to, 1 minus h is going to be negative. When h is negative, the other root is positive. And when h is positive, the other root is negative. Yeah, see, so exactly. Great. We're trying to work through this here for different values of h. But thank you for that comment. when I think about all the different cases, is it okay to consider H as negative? Let me just think about that. Let me just go back to what the setup was and consider, should I only be thinking about positive H's? Like, for example, the growth rate R, that's got to be a positive number. The carrying capacity K, that's got to be a positive number, ecologically speaking. Now, when it says a fraction H is hunted each year, do you think that a negative H is a possibility? Do you think that's what they meant? Let me know if you think negative H's should be considered. Okay, so that's a great question. So I'm going to write that on the board right here. Should we be considering negative values for H? That's a question. What do you think? No. That's what I was thinking too. I don't want to consider negative values for H because that would mean that I'm hunting a negative amount of them, which is adding them back into the system. Now, when I wrote that applied math problem for week 7, if you remember, that was a good one, right? With the constant harvesting, that's when I was saying, like, if the harvesting, oh wait, sorry, that's this week's problem, right? So when I wrote the problem this week, actually, for week 9 applied math, when I had the constant harvesting term, when it's negative, it means we're actually pulling things out of the system. But when the constant harvesting term C in that problem is when the harvesting term in that system is positive, we're pulling things out. When the harvesting term in that system is negative, it means we're putting things back into the system. You could think that in terms of ecology as a way to preserve a species. You know, like how they have like refuges for endangered species, and then they'll try to breed that species and add them to that environment. So in some ways, sometimes negative values for harvesting might be appropriate, such as in the problem I wrote this week for applied math. But so the answer here is nope. Okay, so only H greater or equal to 0 makes sense here. And by that, I really mean that only here, that makes sense. But in the problem I wrote, you'll see that I tried to make sense out of having a negative value for a similar type of term. We're not going to consider that here. We're only going to talk about H is greater than 0. Now, going back to everything that I've seen in the chat, now that we know that H being negative is off the table, we're not going to talk about H is negative. What other values of H are going to make a significant shift in the qualitative behavior of the equilibrium points in this system? By that, I mean, where do you think the bifurcation occurs? So when I set up there that there's 3 different cases for the root for H, those are actually all positive values of H. So there's 3 different cases that all represent positive values of H. And where do you think the dividing line is? Okay. Okay, and somebody has said H is equal to 0.75. That's not exactly what I was thinking, but actually, you know what I want to do right now? You're going to see me kind of like this right now. I want to graph it too, because I think that the person who is talking in there has graphed it, and I want to see what they're seeing. So if you haven't graphed this in Desmos yet, now is a good time, because you're going to see I'm graphing it right now, and this is how long it takes me to do that. Okay, and I'm adding a slider right here right now, and I'm going to zoom in. And actually, I might just share this graph to the chat box for you all so that you can see. Yeah, right. And something crazy happening right there. Oh, did I factor this wrong? Oh, goodness me. Oh, okay. So here's what happened. You're right. Yeah. H is equal to 0.75 is exactly where the bifurcation occurs. And I was thinking it would be H is equal to 1, but that's only because I accidentally factored this the wrong way on the board. So let me take this back. That's okay. That's okay. We all make mistakes. Okay. So how about I don't even try to factor it? Okay. Sorry, that was a mistake on the board. Sorry, I factored it wrong. Okay, I forgot to actually carry the factor of 0.75 through when I so I'm just doing that as a note so that I did that right. Here, let me try again. 7.5 x, and then we have the 1 minus x, and then what we should have is h divided by 0.75. Okay, now that's right, you see, because when I multiply this term by that term, then I get the minus hx that I had before. Okay, so that's the one that's right. Hopefully those notes help people keep track. Sorry, I factored it wrong before. Now I've got it right. Okay, so maybe I should erase the, now people know that I factored it wrong. Okay, and so here's where I still wanted to factor it because I want to see the roots, right? And so now I know that the roots are at x equals 0. And the other root is x is equal to 1 minus h over 0.75. And now I can see where the bifurcation occurs, because the bifurcation is going to happen when this root is a total copy of this root, right? When are these two things going to be the exact same root? And that happens here when h is equal to 0.75. Boy, I'm so glad that you're doing this with me, because I'm making mistakes all over the place. And really, if you're working with other people, that's more eyes on the prize. And so we're going to have less mistakes that way. In case anybody is watching and didn't feel like creating this graph themselves, I'm just going to take a quick minute here to share with you the Desmos graph that I just made. And so you can see what I meant. And I'll just copy and paste this right into the chat that you're all looking at. Okay, so go ahead and click on the link. I just sent a link off to the chat there. And if you do click on that link, that is going to be a graph of this model. And I've put the value of h exactly at the bifurcation point, which is 0.75. But I also put it in a slider mode. So you can see that when h is bigger than that, then one of the roots is over on the negative side. And when h is smaller than that, then one of the roots is over on the positive side. Play along with me here, okay? Get that graph going and play along, because then you can see what I'm seeing. And this is all the work that you got to do before you really, really understand it to the point where you're ready to describe it in a bifurcation diagram. Okay, so there's still 3 different cases, but like we just talked over, there's the middle case here where we have the double root. And that happens at h is equal to 0.75. Okay, you'll see this on the Desmos graph. If you take a graph of x versus x prime, right at the point where h is equal to 0.75, that's where the double root happens. Okay, if you look at the same graph, x versus x prime, for when h is greater than 0, remember that's the only thing we really want to consider, but is less than 7.5, then you're going to see this type of graph, qualitatively speaking. And over here, when h is greater than 0.75, then you're going to see this type of graph. And really, this type of is most nice or play it on Desmos so that you can see it flop between each of the 3 different cases right there in action on a real graph. Okay, so that's why I shared that link with everybody. Hope you're playing along. Does everybody see what I mean there about the 3 different cases? And hopefully everybody feels comfortable analyzing the stability of these three cases. Remember that we're just going to look at the tangent line here. So 0 is stable, and then this one greater than 0 is, oh, sorry, this is unstable and then stable, right? So here's unstable, 0 is unstable, and this one here is stable. Okay, and this one right here, I'll ask you all, what should I write right here? What is the stability of this double root in the case of the double root? Okay, I'm going to do it on either side, but I'm leaving that double question mark for you all. See if anybody wants to tell me what I should call it there for that case. And then over here, this is going to be 0 is stable. On this side, so 0 stable, and then this right over here is unstable. Okay, and I'm reading that all right off the graph because I'm looking at the tangent lines. Node, yeah, exactly. It's going to be a node right in the middle here, and that is, if you haven't noticed, that's a telltale sign of a bifurcation. I don't know if you noticed the pattern yet, but every time a bifurcation happens, every time two fixed points merge together or two equilibria just suddenly appear out of the blue, it always starts with a node. Whenever it's a double root, it starts with a node. No, you didn't. Somebody just said that they noticed, like notice. And then I said, no, you didn't. Oh man, this is too much fun. Okay, so make note of that at the top point of bifurcation, we always have a node. It's a semi-stable and semi-unstable node. Yeah, node kind of triggers the thought that half of it is stable and the other half is unstable. And you can see here that to the right, it kind of has a stable half, right? It has a half. It's half stable on this side. Because if things are on this side, it's telling them to move to the left towards it. But then if things are on this side, it's telling them to move to the left, which would be away from it. And so that this half over here is unstable. Unstable. I can't fit that on there. Duly noted. Unstable. Okay, cool. This is so fun. Make note of it too. Yeah, I'm so glad that we're still having good times YouTube Live. Okay, are we ready to draw a bifurcation diagram? Yes, because now I see all the different qualitatively different instances of things that could happen. And so what I'm going to do on this board now is I'm going to try to draw the bifurcation diagram, but let's all do it together. For example, for this bifurcation diagram that I'm about to draw, what should be on the horizontal axis? What should be on the vertical axis? So open question to you, type it into the box, and I'm just going to erase the board and get ready to draw a set of axes and label them, but you tell me what to label them with, okay? Oh, geez, come on with the typos. X over 0.75. Sorry, there's a typo there again, and that was based off of my factoring typo. The second root is at 1 over h divided by 0.75, not 1 minus h. It's 1 minus h over 0.75. That was just based off the other typo, so we'll still all count it in as the same typo, right? Now, you tell me, what am I going to label on my horizontal axis? What am I supposed to be looking at here? What am I looking at on my vertical axis? You tell me. I'm going to get a drink and take a break while you think about this, because this is really where the learning happens here, is just any idea. It's okay if you're wrong. That's okay. If you are wrong, it'll give me an idea of where any misunderstandings might lie, and that will give us the opportunity to clear them up. So that's why I want to just take a pause and have you try to label the axis. And what would you label that axis? So that you can really understand what is a bifurcation diagram, really. What is it a diagram of? And then I'm going to try to make sense of all the things there by illustrating that somehow in that diagram. So thirsty. X and H. Exactly, right. Now, which one of those things goes on the horizontal axis? Somebody told me that X and H are the things that I need to write down. H is the parameter of interest. H is the parameter that we're manipulating over here. And X is going to be the locations of the equilibria points for the X. Which one of those things should I put on this axis? And for that, keep it aligned with what you've been seeing in the book. For example, I would just invite an example here. For example, take a look at figure 3.4. 3.40. Remember that we just talked about? The diagram that we're about to create is going to be similar to figure 3.40. What goes on the horizontal axis? Same thing that went on the horizontal axis before. H, right. The parameter of interest is what will be displayed on the horizontal axis. Exactly. And then on the vertical axis, we will try to illustrate the fixed points. Great job. Okay. Right. So here, we're going to do H. Over here, H. That's the parameter. Then over here, we're going to do X, and we're going to actually, we're just going to graph the equilibrium points only, right? And H is the parameter of interest. And I'm going to call H the parameter of interest because I just want to note that it's not the only parameter in the system. We also have the growth rate, R, which they ask us to change in part C of this problem. And we have the carrying capacity that we're able to toggle. That's the parameter that we're manipulating. Okay, now because I noted the occurrence, or actually you noted it first, whoever told me H is equal to 0.75 is the special part. Because that's the place where we have our double root, that's going to be the place where the bifurcation occurs. So I'm going to mark that off as a very special place on that graph, okay? Next thing I'm going to do is I'm going to try to draw the location of the equilibria. I'll use blue for stable and red for unstable, but I also want you to draw it too, okay? So hopefully you're also playing along from home, okay? Let's just go by this case by case. Really, there's 3 cases. Let's start with this case here, where we have our usual logistic model dynamics, where we have an unstable equilibrium point at 0 for extinction, and then we have a stable equilibrium point, which is located at 1 minus h over 0.75, and that is a replacement for the carrying capacity. Usually in a typical logistic model, the second, the stable equilibrium point will be located directly at the carrying capacity, but because we're harvesting, that's not going to be at the carrying capacity, which is 1. That right-hand stable equilibrium is going to be located somewhere less than the carrying capacity. That makes sense ecologically because we're pulling stuff out of the system. Okay, so let's see. There's going to be let's do the easy one first. Okay, 0 is unstable. Red pen for unstable. I'm just going to go across the line. Right? Is 0 always unstable? For this case, it is. Yeah. Over here, 0 is not unstable anymore, it's stable. So I'm going to be able to draw the red line right up until the bifurcation point. Okay, so this red line right here is going to be x equals 0, unstable. That's the unstable equilibrium point at x equals 0 for all of the cases of h between 0 and 0.75. Okay, now with my blue pen, I'm going to try to draw the stable equilibria, and that is going to be located at 1 minus h over 0.75. 1 minus h over 0. Okay, all right. And so in this case, for h less than 0.5, we have a stable equilibrium point at x equals 1 minus h over 0.75. Or x equals 1 minus h over 3/4, or x equals 1 minus 4h over 3. I just wanted to get it down to this level so that I could think about it in my head as drawing a line that has a y-intercept of 1 and a slope of -4/3. But you could have also seen that up here, and I don't know which way algebraically makes you understand that better. But for the stable branch that I'm going to draw in blue, I want to correctly illustrate what it looks like geometrically. And geometrically, it's represented as a line with this value. That's why I was trying to factor it earlier, even though I made a mistake. Hopefully you get the point, okay? So, right, it has a y-intercept of 1, and it has an x-intercept of 0.75, and so it looks like this. Right? So this is x equals 1 minus h over 0.75, and that's stable. Okay, and it starts up here at 1. See? It starts up there at 1. Hopefully that made sense. Let me know if anything's not making sense to you here. Okay, so far so good? Right here corresponds to all qualitatively similar situations that are described right here in this first case. Okay? And then the double root case, that's just one single value of h. And so the double root case where the bifurcation occurs, that happens right there. Gonna have to rewatch it a few times. Thanks for sharing. Yeah, and that's totally true. And this is some really difficult stuff. I mean, we're all the way at the end of chapter 3 now, and hopefully you see that bifurcation theory is really a culmination of everything that you learned in chapter 3 about equilibria, stability, basins of attraction. It's all of that stuff. And so really bifurcation theory is kind of the goal in a way. Punchline at the end of chapter 3. Gonna have to rewatch it a few times. That will be good if you do. Okay, bifurcation occurs right here because like we were saying, that's the case of the double root. And then on the other side of it, when h is greater than 0.75, now this equilibrium point, which has the same algebraic expression, has now lost its stability. Really, it traded stabilities with the 0 point. And so I'm going to illustrate that here. That it looks like this. Okay? Okay, remember how 0 used to be unstable? And then after we traveled through the double root, then 0 became stable? Remember that? So where I used to draw x equals 0 with the red pen, after I go through the bifurcation value, now I have to draw x equals 0 with the blue pen because it's changed to becoming a stable equilibrium point. See, so now I have to change that so that here we have x equals 0 is stable. Okay? And what I'm doing here with the other equilibrium point is algebraic expression has never changed. That's not what made a qualitative change. The qualitative change is the fact that after the x-intercept, which is located at the h-intercept of 0.75, after that, that same equilibrium point is now a negative value. So I'm going to continue the line that I was drawing before, but after it dips below the horizontal axis, equilibrium and it positive has now become a double root and then flipped over to the negative side. Okay, so now this line right here is continuing down. Okay, and that's the same line become unstable. Okay, and this is that same bifurcation value right here, 7.5. So bifurcation at h is equal to 0.75. Okay. The final question for part B, what kind of bifurcation is that? And that's going to help you with your concept quiz today. And that's kind of how I started it. I opened it with a warm-up of the difference between transcritical and saddle node bifurcations. And 6, part B. So this is the answer for further exercise 3.6.6 part B. Okay. What kind of bifurcation is that? In which two equilibrium points merge together and become one just for a second, and then coming out the other side, they have swapped their stabilities. Transcritical bifurcation, right, yeah. So this is a transcritical bifurcation. Great job. You're doing great. This is some tough stuff. So good job. You're hanging in there. That's right. It's a transcritical bifurcation that occurs when h is equal to 0.75. And just as a side question to you all, what's special about 0.75? I mean, I know it's the bifurcation point, but what is the value 0.75? Is that, what is that representing? As we go back and read through the problem, that was actually of a special value in the opener of the problem. So what else does 0.75 represent in this model besides being the value of h at which a transcritical bifurcation occurs? What else is special about it? Rereading the problem. The answer to that question is in the opening sentence of the problem. And the reason I'm asking you that right now is because in part C, it asks us to change R to 0.5. And I'm like, why the heck would you make me change it all right now? What are you trying to do to me here? Right, 0.75 also represents the rate of growth. Right, value H. It also represents the rate of growth. Right. It's the same as the growth rate. Right. And so that's kind of the secret to this problem, is that it's also representing the bifurcation occurs when the fraction of the population being harvested is exactly equal to the growth rate. Now think about that ecologically speaking, right? Because the growth rate is the constant per capita growth rate, right? We've learned that since the beginning in ecology and mathematics. When I talk about R, that's a constant. X prime over X is equal to R. That's the per capita growth rate. And H is supposed to be the per capita harvesting rate, right? Because it's minus H times X. And so the fraction that I'm harvesting per capita is H. And so when the per capita growth rate is the same thing as the per capita harvesting rate, that's when we get a bifurcation. And when the per capita harvesting rate exceeds the per capita growth rate, that's when we're in trouble, right? Because that's the place at which the extinction equilibria becomes stable. Okay, so can anybody summarize that in a lesson that you would tell anybody who's trying to manage a game farm or like a hunter or something like that? How would you explain that in a layperson's term, what I just said. Oh, thank you. Somebody has to sign off. But thanks a lot for participating. And I'm loving these live sessions too. I wish we could just keep doing this for the rest of this book. This is so much fun in here. But maybe later, maybe sometime in the future. Anyhow, going back to what I was saying, the relationship between harvesting rate here per capita and growth rate per capita. Can anybody summarize that in a lesson? Because I'd like to write something up on the board there, but I think it would be just wonderful if it incorporated your words instead of just me. When harvest rate exceeds rate of growth, population will die, will decline to 0. Exactly. And that totally makes sense. So finally, math that makes sense, right? I bet my dad would say to me, well, you didn't have to do all that math to tell me that. But sometimes I would come home from being a math major and tell him all the stuff I learned, and he would be like, okay, well, the punchline makes sense, but the rest of it doesn't. So, yeah, totally. You have to keep the harvest rate below the growth rate or the population's going to die. Now, the last thing I want to do after I write that down is that I saw some requests come in to go over the over-under method. And so what I'd like to do is try to go over the over-under method a little bit for this exact problem, because we've already been studying this problem, and I'll show you how that method could be applied to this problem. Okay, but let's just start with that lesson that you all are saying, and I don't want to steal your words. I just want to highlight your great student understanding of this. And it says, keep the harvest rate below the growth rate or the population will decrease to 0. Okay? So harvest rate must be below growth rate or the population will go extinct. Okay, that's our takeaway message from this problem. Let's check out the over-under method. I think it would be a fun way to illustrate it right here on this problem that we're already talking about. So now let's look at the over-under method. Okay, and how to start the over-under method would be to just copy down the, I'm going to copy down the equations again, but I'm going to use different colors. Okay, I can't remember what I used first and second before. Okay, I see, right. So I'm going to use blue for the logistic term. So we have 0.75 times 1 minus x in blue, and then minus hx. Okay, so harvesting term right here, and we're going to have our logistic growth term, logistic model. Okay, so we got, now we're just going to go over the over-under method a little bit, and I'll show you how you can get the same result that we just got here in this bifurcation diagram, but using that method. Oh, you caught me again. I'm so glad you're watching. Thank you. I don't know what's up with me today, but I made the same exact mistake twice on the board. Thankfully, I have a really great students here with excellent attention to detail. Thank you. Times 1 minus x. Okay, right. Now, remember the over-under method, just to summarize what it is it's a method in which we break apart the differential equation into 2 different terms. Instead of graphing the whole thing at once and looking for where the roots are, we break it off into 2 different terms, and then we graph each of those terms separately, and we see where those terms would intersect, right? Because if we look at the blue and the red separately on a graph, and we see where they line up, that's going to be the place where x prime is equal to 0, okay? So in this method, x prime equals 0 when the blue graph intersects the red graph. Okay, and then after we locate the equilibria by reasoning where the logistic model meets the harvesting term, then on either side of that equilibrium point, we're going to talk about who's over and who's under, and that's going to tell us the stability. Okay? And usually, this type of method would be implemented when the algebra becomes just too much to handle. And we already talked about that on Tuesday with the spruce budworm model, when we went through it and we pretended that it was doable, and then we hit several walls. Remember, we hit a wall when we realized we had to use the cubic equation. We hit another wall when we realized that to take the derivative for linear stability theory, we need to use more complicated rules. So usually this method is used when the algebra becomes too much to handle. It's kind of a geometric way to do the same thing, but it's fun to just look at. And this is totally an appropriate model to do it on, because the thing that you want to do this kind of model on is something where you have two naturally separated terms. Here we have logistic model and then harvesting term separate. In the spruce budworm model, same thing. We had logistic model and then we had density dependent predation, right? So you want to do it on stuff that has like those two separate parts with a big minus sign in between. That'll give you a hint that maybe this is an appropriate method. Okay? And so what we're going to do is we're going to do our typical graph where we would usually do x versus x prime, but I'm not going to graph x prime. I'm going to graph two different model where it's 0.75x times 1 minus x, right? Because that has roots at x equals 0 and x equals 1, the carrying capacity. And then separately, we have this other thing where h is equal to x. Okay, and so here is one case where h is equal to x. This red line here is hx, and this is a case. I'm going to write it in black to make sure that you can read it. This is the case where h is less than 0.75. Okay? Now, remember, the over-under method, I'm going to cleave it off into two different parts. I'm going to look for the places where those intersect. Do you see why I know that this is the case where h is less than 0.75? Because that was the case where I was going to have two equilibrium points. One was going to be at 0 and the other one was going to be at positive value. And so the fact that they intersect right here tells me I'm in that same case like I had drawn before. All right, so here's one equilibrium point, right? So here's one. And then here's the other equilibrium point. This is the x equals 0 point, and this is the x equals 1 minus h over 0.75. Okay, so what this method does is it locates the equilibria as the intersections of the two colors, and then it allows us to understand stability by talking about whether x prime is positive or negative, right? Because if x prime goes from being negative to positive, that means that its derivative df dx is positive. So if I'm going to go from x prime being negative to positive, that's an unstable equilibrium. And then vice versa, if I'm going from x prime being positive down to negative, then that's a stable equilibrium. Okay? And so because I have two equilibrium points here, it cuts it into three different regions. Region 1, region 2, region 3. Okay? And right here in region 1, okay, red is greater than blue. So x prime, since red is greater than blue, it means that this is bigger than that. So x prime is less than 0. Right? And then over here, in region number 2, blue is greater than red. And so x prime is region number 3, where red, again, is greater than blue. And so x prime is less than 0. Okay, I could do this again for the other cases, but I probably shouldn't because we've already been spending quite a lot of time here. But I hope that you get the idea, which is that in this case, we see 2 intersection points, right? And we can talk about the stability of them by saying whether x prime goes from being negative to positive or going from positive to negative, okay? Just to remind you of what the x versus x prime graph looks like. So this is what I had drawn for that first case on the other board back when I had all 3 cases on this board, right? And remember that I classified the stability of this as unstable and that as stable. And it's the same thing the over-under method is telling me here. You see, because region number 1, red is greater than blue, red is over blue, means x prime is negative. And this is just kind of a side graph, right? This is just us remembering what we did before, okay? And from what we did before here, do you see how I'm reading off the graph the fact that x prime is negative? That's the same conclusion I get for region number 1 with the over-under method, okay? And then in region number 2, the over-under method tells me x prime is positive. And if I had gone back and referred to that same graph that I had drawn before, you see x prime is positive that whole time in region number 2. Okay, and then finally region number 3 over here where red is over blue, you see again the fact that x prime is negative. So it's the same thing as the analysis we did before, but sometimes it's just naturally the red model where you just have such complicated, algebraically complicated terms that you don't want to deal with stuff like the cubic formula. I hope that was enough. I know that time is getting on. We're almost at 2:45 here, so unless somebody tells me to please do that again for the other cases, then I will just leave those other cases out. But it is fun. If you wanted to explore it on Desmos, it is super fun because you can see that as h increases, I can't resist. I just have to draw the bifurcation value. On the over-under method, when h is exactly at the place where it's tangent to that parabola, that's when you get the bifurcation. Okay? So right here, I'll draw it with a dotted line. Okay, so this would be h equals 0.75, and this would be the bifurcation value. This is the bifurcation value. Right? You can see that the bifurcation happens when the red part of the graph is exactly tangent to the blue part. And actually, in a way, it gives me a totally separate, different way to find the bifurcation. Because if you're really inclined to do calculus, you could say, well, let me take that blue parabola and take its derivative, df dx, and evaluate that derivative at the equilibrium point x equals 0. And that's going to tell me exactly what slope I need to have on the h to be exactly tangent to the graph. And then if I raise that value of h even further, then you can see that the red line would intersect the blue line on the other side, on the negative side of x. And that's what all we went through before. Okay, hopefully that was helpful. I know it's been really long, and I also know that I've already made a video for the last request on the list, which is 3.6 further exercise 2. But I want to give anyone who's left watching an opportunity to ask any more about that question. I don't know if you watched the video for it and you still have questions, or you just asked that question without having watched the video. I'm hoping it's more of the first side because it would probably take me half an hour at least to go through that whole problem on the board. and I know that we're already kind of close to the 2-hour mark, but I still want to help people who have already tried and are still struggling. So I just want to give you an opportunity in the chat box here. If anybody wants to specify a certain part of further exercise 2 that they have an issue with, or some question that you want to raise about it, go ahead and enter that in now. Otherwise, I will say to that problem. Can I give you a minute while I take a drink of water? If nobody else asks about that, then I'm going to let you go because it's been a while. Almost out of water. It's been so long. Thank you for the math-a-thon. Thank you for the puns. They have been very punny, and I do appreciate it. It is the lowest form of humor, which is to say the most understandable form. Even my 2-year-old enjoys a good pun. I'm good too. Okay, thanks for watching so much. I appreciate you being here. And no problem. We're going to be making those jokes for the rest of the day now, aren't we? I'm so glad that this has been helpful. And this has really scratched my itch for feeling like I want to be in the classroom with you too. So thank you so much for just making this happen. This has been a wonderful experience. And I probably might continue online teaching again for a while just to support those who want to be in a classroom, but for health reasons might want to avoid large gatherings. So if you're interested in any other class that I'm teaching, I'd love to have you again. And thanks for being here. Bye. Have a nice day.